Hello everyone. Today we have a new lecture seminar. Today's speaker is Feng. He is a doctoral student here at UIUC and he also received his master's degree from here. He's under the supervision of Professor Harold Tutumler, and he did his undergrad in ZJU University. His research focus is railway substructure investigation, and he used both numerical modeling and statistical analysis. And I want to take this opportunity to congratulate Professor Tutumler and his research group on winning the 2019 AFP 00 section for Best Paper Award.
Okay, hello everyone. So my name is Feng. I guess many of you already know me. So I'm a second year PhD student working with Professor Tutumler. And today I'm going to present findings from a project that are joined by UIUC and ZJU, which is my undergraduate university. So as listed in the title, I'm going to discuss the ballast used for high-speed rail corridors and repeated loading simulations of the full-scale ballasted track separate experiments was conducted at ZJU high-speed rail tester facilities. So we have Professor Tutumler, Professor Hashash from UIUC, and Professor Bien from ZJU to working on this project, and along with also 4 graduate students. So here is my table of content. I'm going to make an introduction and the motivation behind this project, and then I will present the full-scale high-speed railway tester, and along with some of the preliminary experiment results. So then I will introduce DEM and some implementations for the railway simulations. Then using this DEM, I will present the results for the simulations, and followed by some concluding remarks and our ongoing phase 2 research. So yeah, high-speed railway network in the world has experienced a rapid development in the world. So actually, especially in China, like around 66.3% of the high-speed rail in the world is in China. And by the time of 2019, in China, we have already exceeded 31,000 kilometers in high-speed rail. So in the USA, an incremental approach was taken to upgrade existing passenger railway corridors. So when we're talking about high-speed tracks, we have 2 options. One is the ballastless track, and the other one is ballasted track. So for the ballastless track, the pros are it needs less maintenance and has a great ride performance and stability, and it also usually have a long durability and service life. But on the other hand, it requires a higher cost for the construction, and the track improvement is limited for this type of track. And usually we cannot lay these ballastless track in complex site conditions. So on the other hand, for the ballasted track, it will have a lower cost in construction, and the track improvement is available after the construction. And because we are using unbound aggregate materials, so the good drainage performance can be obtained. But also it has its own cons, as usually compared with the ballastless track. Ballasted track will have a lower and inhomogeneous stiffness, and it will require a frequent maintenance on the track. And compared with ballasted track, it will have a pretty higher noise level, and also will experience problems of ballast flight when running with high-speed rail. So as we can see, both of these approaches would have its own pros and cons. So the ballasted track was selected for the high-speed rail network system that extending to the western part of China. So a better understanding of the ballast behavior on the dynamic loadings is required. So when we're talking about the ballasted track, there is a rapid deterioration of track structure and increased cost of maintenance activities that will be mainly resulted from the degradation of the ballast layer. So below are the 4 common problems we will encounter when we have the ballasted track. The first one will be the ballast degradation, and then we can also have differential settlement, and also as well as pumping or insufficient support as the last one. So when we use the unbound materials, the ballast material, the unbound ballast layer can facilitate a drainage and provides a good substructure support for the railway system. So understanding railway ballast vibration and deformation behavior is important for us to have a adequate design, construction, or maintenance of the track structure. So in this project, the full-scale experiments was conducted in DJU ISHRT facility, which was located in China, and the numerical simulation was done here in UIUC using the DEM software called Block 3D. And as for the full-scale field test, it is not involved in this project because it is usually very expensive and labor-intensive, and usually consists of very complex components, which makes it hard to control the process and the results. So let me talk a little bit about this DJU high-speed rail tester. And the equivalent vertical load applied on the ties was obtained from the train track soil coupling analysis model. This is a model that proposed by Professor Bian in his PhD thesis. And there are 8 actuators was used to simulate a train passage at any speed. And there are the rail segments are installed on the transfer the loadings from the actuators to fasteners and our concrete ties. So here is a picture actually taken in DJU Ziyingang campus on November 2017. You can see on the left is Professor Tutumula, and on the right is Professor Han Shash, and in the middle is Professor Bian. And in the front of this picture are the 8 actuators that we use to do the lab experiments. So this photo was taken during the time when our phase 1 research was taking place. And now further continuing our professional collaboration, we are now working on the phase 2 of this project. So back to the model. Behind the 8 actuators, there are a physical model that consists of rail, fasteners, or concrete truss ties, and these are placed on top of the ballast layer and the sub-ballast layer and the embankment and the pile foundations. So for this model, the vibration velocity sensors and all other sensors were mounted in the model to capture various dynamic responses from different layers. So here is some preliminary test results we obtained from the lab experiments. The vibration velocity was measured for the ballast surface, and as you can see, the velocity meter was mounted on the center line of the ballast structure. This is indicated here as the V4 location, and at the bottom are the vibration velocity measurements that we obtained at 3 different speeds using this velocity meter. So also we obtained the vibration velocity of the concrete cross ties, and as you can see, the vibration velocity meter is mounted on the tie, and as the same as before, these are the vibration velocity results obtained at 3 different speeds. So besides the vibration velocities, in the lab they also obtained the dynamic stress on top of each sublayers. And these are the 3 dynamic stress obtained on top of the sub-ballast layer and at 3 different speeds. So apart from the laboratory works, numerical studies can also enhance our understanding of complex ballast behavior. So usually there are 2 approaches. One is a continuum approach, and the other one is a discontinuum approach. So when we use the continuum approach, we usually assume that the granular material will fill the space of the occurrence. So it is usually computationally efficient, but mathematically it will be complex. And for the discontinuum approach, it can model the behavior of individual particles. And it's like the reverse turn light. It will be mathematically kind of straightforward, but it will be like very time consuming to do the computation. And this is usually we refer to as DEM. So the 3-element model, also known as DEM, is a good way to capture mechanical response that are unique to granular materials. And because in DEM, we explicitly consider the particle interactions as mass spring damper systems. So this will be ideal tool to capture the vast layer behavior. But as I mentioned, like this is due to its particular nature of how we do the calculation, do the computation in the DEM. It will be computationally expensive. So the whole loop or whole calculation flow of DEM can actually be summarized very simple, like in 3 steps. First, we start with the force update, and then once we obtain those updated force, we can update our acceleration, velocity, or positions for our particles. And once we have updated all these mechanical and geological information for the particles, we can do a neighbor search and then a contact detection to see like which particles are interacting with each other. And then once we have found like those particles are interacting with each other, we can again update the force again, and this is going to be a loop to do the calculation. So as I mentioned, for DEM, it is usually computationally intensive. So this is why where the parallelization idea comes to mind. And so Professor Hashash and his research team has developed the parallel version of Block 3D. And this is a shared memory parallelization algorithm that without domain decomposition. So once we have this parallel version on the 100,000 particle benchmark simulations, it was able to reach like 28 times faster using 48 cores compared with a single core simulation. So also, Eun Park, who was a PhD student in Professor Hashash's research team, was able to, using this parallel version of Block 3D, to run the largest DEM simulation in the world with 52 million polyhydro particles. So these are some of the results like I obtained from his PhD thesis. And once we have this parallel version DEM available, we need to obtain the particle informations, and then we can use this enhanced UI aggregate image analyzer to obtain the grain scale properties, for example, as the angularity index, which we'll use as an input for the DEM simulations. So using Block 3D, we have already done some great work on railroad simulations. For example, Feng on 2010, he has conducted simulations for ballast Dirac shear test. And Qian on 2014 has done a simulation for ballast triangle shear test. And the whole on 2018 has run the full scale DEM simulations on ballast tight sport conditions. And she was able to visualize those stress in the ballast and the force change in the ballast layer. And recently, we have also been working on using DEM Block 3Ds to analyze the different sport conditions and how those different sport conditions will influence the particle movements and as well as for the force propagation in the ballast layer. So back into this project, we have some implementations into the Block 3D for the railway simulations. And the first one is loading functions. So in old times, we usually use sine functions or like a combination of sines to simulate the actual field loadings. But now, once we have these loading functions, we can given the data to the DEM, and then we can apply this exactly same force as applied in the lab to be applied on the concrete tiles in DEM. So this is like the loading functions. And once we have these loading functions, what we want to make sure is that the applied force the force applied on the tile is the same as the reaction force made by the ballast particles. And this is where the second implementation of PID controller comes to mind. The PID controller represents for proportional integral derivative controller. And it is a control loop feedback mechanism to apply the target force. So the controller will decide what's the magnitude of force to be applied on the tile using a feedback arrow. So as we can see, like without PID controller, the blue line is the applied force we want to apply it on the tile, and the green curves are the actual reaction force given to the tile by the ballast particles. And without PID, you can see those lines don't match very well. Actually, the green curves are like jumping all around the area. all over the place. But once we have using this PID controller, we can see the blue lines and the green lines are pretty much identical. And this is what we want for our DM simulation to have this feature. So once we have those two implementations available in the DM models, we will have the particles used for the simulations, and the particles will have the same grain size distribution as used in the laboratory experiments, and those polyhedral particle shapes will be used to capture the realistic behavior of this bias layer. And also some of these are the inputs for the DM simulations that we use. So overall, there are 170,000 particles in the DM model that was generated and stabilized. And 8 concretize was also placed on top of the ballast layer. And the dynamic loadings, as seen here, are applied on different concretize, but with a time differences, because we are trying to model the train moving on 2 different ties. So once we have this model ready, we will compare the concretized vibration and the ballast vibration from DEM and the results from the full-scale test measurements. So for the concretized, the vibration velocity was printed out at the center of concretized, so which is here. And for the ballast vibration velocities, a imaginary cubic was printed out to print out those like particles inside this imaginary cubic, and we use those data to compare with the lab measurements. So overall, there are 3 different dynamic loading patterns applied on concretized to simulate train speeds, and the magnitudes, as you can see, for these different speeds are the same, but the frequency will be of the loadings will increase as the train speeds increase. So now let's compare the cross-tie vibration velocities. The black lines are the measurements we get from the lab results, and those red lines are the simulation results that we get from the DEM models. And we can see that overall it is a good match, and we can see that both the magnitudes and the trends have a good correlation or good match comparing these 2 results. And in terms of the ballast particle vibration velocity, again, the black lines are those measurements from the lab, and the red lines are those measurement simulation results from the EM model. And overall, again, we can see there is a good match that was achieved, but the particular nature of bias behavior will still be need to be further investigated to say more about these comparisons and say more about the mechanics inside the bias layer. So again, here is a particle response animation that we made, like for under a train moving. At this time frequency, at this time step, we can see the train wheel is moving through the cross tie number 2 here, and those black arrows means the particles have the velocity moving upward, and those red arrows are the particles moving downward. And we can see like most particles near concrete tie number 1 has a tendency to move upwards, and the particles near cross tie number 3 has a tendency to move downward. And we have a mixture behavior for the particles like near concrete tie number 2. So now we can see as the train continues to move, those response will change in the bias layer. As the train moving further, we can see that different response was given to the bias layer. And once the train has passed, or during the rest period, the bias layer will go back to a stabilized condition again. Okay, so now this is the settlement measurements we have for the ZJUI SHRT experiments. We can see this is the accumulated settlements that measured on top of each sublayer at 3 different speeds and 2 different loading magnitudes. And you may notice that at the speed of 300 km per hour, there is a significant increase for the accumulated settlement. And both regardless of the loadings, because you can see this is is a large jump here, and this is pretty much a large jump as well for the 22-ton loadings. So this is kind of because of the speed effect the base layer is experiencing at a higher speed. And so that concludes our research for the phase 1. And for our current phase 2 research, we already have constructed a new full-scale ballast track that was in the CJUI extractive facility. And we also will have some new type of sensors installed in the track, for example, the smart rock. So the smart rock is actually a 3D printed items that try to simulate to be the same as the actual rocks. And there are some sensors will be hidden or like mounted inside this 3D printed shell, and then this smart rock will be put into the ballast layer. So it can actually, in the same time, measure the individual particle responses in the ballast layer as the experiment continues to do. And so we also will have a more thorough track settlement measurements for DM simulation as well, for us to do the comparison or the analysis. So now I can have some concluding remarks. So for the ballast layer behavior on the high-speed rails, we have shown that it's important. And there is the repeated high-speed loading test that was conducted in CJU. And we have implemented some of the loading functions and the PID controllers in the DM software. And using those functions, we will be able to run the large-scale track simulations like DM. And we also show that polyhydro particles in polyhydro particle EM simulations can capture the ballast behavior. And as for also we have a new experiment data and simulation studies for our phase 2 research. Okay, so that's everything for my presentation. I can take the questions.
Yeah, a question about loading system of the full-scale testing.
Yeah.
How you simulate the different speeds of your high-speed rail that you're loading?
So yeah, as I mentioned, this is a model that developed by Professor Bian in his PhD time. So they have already a numerical model available to simulate the field loading conditions, and then we obtain those trends and apply to the actuator.
Okay.
Yeah.
So are these photo measured and validated using the field data?
Right, I think so. This is back in 10 years or more ago. So this model has been already quite well validated. So that's why we use this as a qualified model to obtain the field results, field loadings.
Oh, thank you.
Yeah.
So here you showed, if you can go please back to the slide that you had the loading. You're showing the pulses that you are including in your model.
You mean in the beginning?
Yeah. Not, yeah, it's here.
Or
Yeah, this one is one example. So here, how do you make sure that this is actually the loading? Because let's suppose you have a weaker material that is underneath it. It might create some dynamic loading, not dynamic in the sense of dynamic analysis in which the loading is like a pulse, but as a load that might differ, might increase, especially that the load might be high for high speed, especially
you are right.
for
So
cargo.
that's why we have the PID control to control the force we applied is the same that we get from the reaction force. And so we apply the PID control in our DM, but also in the actuator, in the lab test, they also have the PID server to control that we do apply the force we want, and we do get the reaction force at the same.
Yeah, I totally understand what you're saying.
Yeah,
my question is a little bit different. My question is, you have the loading that's being applied, and you have a pulse, right? Sometimes if you have a weaker spot or something, it might move a little bit more, which creates some additional dynamic loading other than the static, not static as if it's static, but it's the load that is not changing. It might increase, which is the dynamic effect. Other than the dynamic analysis that you're mentioning. Like for example, in our case, for the highway roads,
Yeah.
if it's rough, the load might increase up to like 70% of the initial load because of the impact. Is this an issue first in railway, and if yes, how are you considering it?
But in the lab, the bath condition is always the same. So
Let's think about the field. The field.
yeah, in the field, then we should have like a different responses to capture those like the dynamic impulses you are talking about. So, but like in here, because we only are doing the test in the lab, and we want to control the force we apply. Otherwise, there might be like some impulses in the field, but we don't consider that in the lab. Like.
Well, let me take that question quickly because I think I know the answer what you're intending to hear. I think. Usually what happens is if you think that everything is smooth and there's no flat wheel is perfect and rail is perfect and you're applying just the wheel load smoothly with train running at different speed, right? In that case, you're assuming that there's no actually impact load. That's something called an impact load, what you're referring to, I see. We know that happens a lot according to the terrain as well as the flat wheels and things. So there are wild detectors, they call now. Many locations in the US, you will find it, railroad network, those wheel impact load detector. Wild is the short for that. They're already established, and that's how they measure. And actually, in our rail tech, back in 2010, there was a person, Brandon, who studied this. And we have clearly shown that up to 3 times as much load levels than typical static wheel loads, right, standard, can be applied because of such dynamic impact load conditions. But if you forget about impact loading, now just the effect of the speed, and this was clearly observed in this experiment, which is a really clever experiment, again, innovative test of it. By going from 100 kilometers to 300 kilometers per hour, they see that 30 to 40% sometimes increase just the response, dynamic amplification factor, we call it. Now, if he goes back to showing you the settlement records again, how the speed plays a role in the settlement, especially when you go to 300 kilometers, 300 kilometer speeds, you see the high rate of accumulation of settlement. That's purely dynamic amplification result. That's what happens because of, again, high speed and continuous rotational principal stresses, basically settlement increase. That's not impact load though. On top of that, there is the impact load that you're asking.
Yeah. Thank you for that.
Yeah.
Could you elaborate a little bit more on the modeling of the DEM? As in, is every particle a point unit, a damper spring unit, or how is that modeled?
Yes, so the interaction between particles are modeled as damper springs. I can go back to the slides. Yes, so as you can see here, like those individual particles are modeled as rigid parties. So they don't deform or like have like crack something. But between them, the interaction between particles are modeled as these mass spring damper systems. That answers your question. So like basically we have like 100,000 particles, and each particles will have some certain interaction with some particles, and those particles are all modeled as this type of spring damper systems. And then during the loop of the DEM, we will update the force and then update the accelerations of centrals based on the force we have get. And those forces are calculated using these spring damper systems.
I have another question. So here, how do you? I understand how like the DEM works, but how do you take into consideration like the environmental, like weather condition? Does it have an impact on this bonding, or whether also the age with time, what happened to the aggregate themselves?
So for environmental, if you're talking about temperature, then
Not with temperature, maybe like water. I don't know if there is no like good drainage, maybe it might.
but
accumulate.
we don't like model water inside the DDM models because water is kind of like continuing thing. So usually we don't model the water in FEM, but we do have like falling particles, and to model those falling ballast layers, we can change the parameters we input into the DM model. For example, we have the friction angle to like calculate how these particles interact with each other, and then we have one value for fresh ballast, and then for the fault ballast particles, they will have like a different friction angle, and so by changing those parameters, we can model different conditions of the particle parts.
So you change the friction, but you keep the shape the same.
We can adjust the shape. Like if we say like after some time, the particles will sometimes break, then we can create a new model with different gradations. But yeah, you are right. We cannot change the particles like within a model. We can only like establish a model with different gradations.
But just a follow-up question, how did you take into account that deterioration?
I'm sorry, what?
You mentioned some options of how you could do it.
Yeah.
But how did you do it? Take into account the deterioration. Did you change the particles for smaller particles and fines?
Yes, we can change, like based on the angularity index, we can change the shape of the particles. That's one approach we can do. And the other approach, as mentioned, like we can change let me see the slides that I have for the particle inputs. So as you can see, these are the parameters we input into a DM model. And so for fault ballast layers, we can change this interparticle friction angle. So the 31 degree is for fresh ballast, and we used to do the experiment to be 27 degree. That is for the fault ballast. So by changing these parameters, we assume that this is a fault ballast.
Based on what did you determine that change?
We compare the results with some lab experiments, and we do some experiment we basically try different friction angles and see which friction angle represents the same trends. And then we determine, so this is a parameter we want to use for the ballast.
Thank you.
What do you use as a support for the ballast, underneath the ballast? What's the condition that you put for boundaries?
So in DM, it's a totally rigid boundary.
And how is that accurate? I mean, how the impact would be if you put it, for example, like a certain condition of maybe like the simplest one can be like springs, like a spring foundation.
So it would be difficult for us to like have a springs underneath the
So just one example, but
yeah.
how is the impact of assuming that you have rigidity, especially if you have weak subgrade or weak soil?
Right, you are right. If we are talking about like weak sub-ballast layer, then there will be like some settlements happen in the sub-ballast layer. But this is not something that we can take into consideration for now, because when we have a sub-ballast layer, then we will require a huge amount of particles to be used to represent this sub-ballast layer, right? And usually sub-ballast layers have a smaller size, and then which means the number of particles we're gonna input will increase. And for that, the time that we take to do the calculation would be to do the computation would be too high. Usually we're gonna take maybe months or years to finish it.
I understand.
So that's like one of the limitations if you want to use. So that's why I only stick with the ballast layer instead of like the whole system of the track.
But can't you within the DM create some sort of boundary conditions at the bottom? I think you don't need. You might be able to overcome this by putting some sort of a boundary condition at the bottom. That can be like spring foundation or something. I think you can. It will not increase the computation.
Yeah, if we put the springs and those we assume those layers as a spring composed of springs, then we can do it. But right now we don't have that function yet.
Okay.
Well, Professor Hai Huang built a FEM-based green function foundation, which allows the soap foundation, remember? That affects the whole damping coefficient of the dynamic reaction of the ballast. So they studied that in their papers.
Yeah, so it's like the interaction between those FEM. But this requires, actually, I think it's also requires a long computation time to get back as a loop.
I have a question if you have time. So I'm not sure if I missed, do you analyze this for a specific time duration, or do you assume that the particles will remain intact for the entire time of analysis? Like the degradation of the particle is happening during the analysis? Like for example, you said that we can change the parameters if there is a fouling or those kind of effects. So when you're looking at the impact of speed, do you also consider like the degradation happening, or is just like everything is the same properties of the material?
So during simulation, everything has the same property.
Okay, but can we also, do you think that with time, if you see how the response will be?
So the way that DM works here is like we have input file, and then we specify a certain time period, and then DM will run, and then they will output a restart file that saves the last condition of these simulations. And based on this restart file, we can change the parameters and then continue with another new simulation.
I guess the question is, can our particles break in this simulation?
No.
So the gradation doesn't change throughout the simulation. But he already answered that. But anyway, so the idea of whether it's necessary to model crashing, because crashing always requires a priority function on how individual rocks will crash into how many pieces. So that's something you have to also program in.
Yes.
And that has to come from some probabilistic and supported with experiments, right? That's something for about a decade we're debating now, back and forth, whether that's needed. Because when you think about the life cycle of the ballast, it's the most drastic change you can imagine. The layer completely changed from being large rocks to a well-graded gradation. Really huge drastic change as it becomes older used ballast like that, right? So now, first of all, how can you model in one simulation all of that throughout life cycle process? Secondly, you have to, again, dictate on that, and that's very hard because it depends on the breakage, depends on the mineralogy of the particle, the forces, contacts, the layer assembly, everything else. So we know that's what's happening. Why not go and pick certain locations, let's say it's 10-year life cycle or a life period or 20-year, different gradation at different stages of life, and take those and look at their formation behavior of different compositions, right? Bring them all together to understand it. So that's kind of where we're moving towards. Early on, we got many questions on this approach, like, oh, but your DM approach cannot break particles, right? But now I don't feel like we need to be even modeling that, because that's too much of a guessing game anyway. What we know for sure is how the gradation changes throughout the life. So why not pick the certain periods of the life of the ballast with different gradations and understand the deformation behavior related to those, bring those together. So I think that's the approach most of us are pursuing.
But then still we cannot answer that question of the life cycle, let's say.
No, we can't. It's a fact. It's out there. Well, but quite a bit changes according to the condition of the loading.
Right.
And special track locations that actually get pounded more with loading. Actually, the ballast life is much shorter. Maintenance cycles are much more frequent. Things like those. So understanding that from the field and bringing into realistic modeling is needed. there's a lot going on the maintenance end of actually how in the field deterioration is happening.
How do you take into account like I understand like we asked the same question which is related more to a design side which is here more of an analysis of the stress distribution and the strain distribution within the balance. But we were trying to see if it can go to a mechanistic design at the end of the day by applying it multiple times and see how it degrades. But my question is here, how do you take into consideration here also the compaction, like the construction quality? Do you take into account like maybe the way that they are compacted?
Yes, we can compare the void ratio that in the lab. They can measure the void ratio for that the model, and then we can do the same compaction in the DM and to measure how the void ratio is whether the same or not. And once we have reached like the same void ratio, we'll say that they have experienced the same compaction efforts.
Okay, so you look at it from perspective.
Why don't you answer then why we needed the second phase experiment and what are we doing now in the second phase experiment to actually get all of that correctly? I think that's an excellent question. That's why in the phase one we couldn't do this.
Yeah, so we actually can see from here that, like as you mentioned, that about the conditions of the ballast. So if you like take a notice here, even though they have showed the correct trend in the accumulated sediment, but overall the magnitude is only up to 6 millimeter, so which is minor, too minor for us to model anything. And that's because when in the lab in DJU, before they do the measurement of the accumulated sediment, they have already put some loadings on top of the tile. So those initial sediment happened in the tile was not recorded. Like say, I don't know how many like cycles they have run, but say they have run 2,000 cycles, then there will be a huge initial sediment that already taken place. So the ballast layer was already shaken down, and then they started to do the measurement. So even though it shows like the correct trend, but like the magnitude is not the same as we should be expecting in DM models. So that's why we want our phase 2 to construct a full new ballast track, and then we start the measurement as the beginning. So from the initial conditions, we have a fresh ballast. So nothing was settled and nothing was shaken down. And then at that time, we started the measurements. So that's the same condition we are trying to match in DEM as their newly construction ballast in the lab. So once we can make sure those conditions by comparing different properties as the void ratio, then we can say, oh, these two are at the same condition, and then let's model the settlement and compare them between those two. So that's why we have this phase 2 project.
How many of the sensors and what kind of response do you get?
So there are overall 10 sensors. 8 was underneath the tie, and then the 2 was between the ties, but also installed in the ballast layer. And then those sensors can capture the velocity and the acceleration, and also like the rotation velocity or the rotation acceleration of the particles.
Here's my question.
Good luck with that.
And this is a question for everyone to think about, because this is a challenging question. Imagine those rocks, like, again, these are 2 to 3 inch rocks, right? That's fresh ballast. That's how you build the railroad track ballast. What would be the void ratio or density? How can you come up with that correctly, accurately measured in the field from the construction? When you say that the ballast is done, now it is ready for trains. How do you decide that the compaction construction related density and compaction densities or void ratio, whatever, right, can be actually determined, measured, and obtained, and that's an input for your model, right? You need to match the initial conditions to start, especially for settlement calculations, predictions. How do you get that in the field correctly measured? That's the million-dollar question for you and for everyone. It's still being researched.
Well,
Any ideas?
I would say, are we allowed to destruct the layer.
What?
How we allow you to like take in some samples outside.
I mean, how do you do sampling though? I mean,
You would disturb it anyway.
Right.
you cannot use your nuclear gauge or whatever, right? No
No.
way.
Maybe we can maybe we can try GPR.
We have a GPR, let's use it.
You measure, well, I know you measure density with GPR for the asphalt mixes and stuff.
Yeah.
Yes.
This is nothing like that. This has 43-45% porosity. Okay.
But-
How do you do that?
But can we can we develop like a mixing theory for ballast materials? That's the way we did for
It's
asphalt.
simpler than that. There's no mixing. It's like a bunch of stones sitting, very large stones, like the ones again. You sound in this box in the lab, right? This
Just,
large.
so it's just like big rock boulders and big air.
Yeah,
air
how they
blade.
pack and how they establish the ballast layer. But how do you get the void ratio or the density of that?
Because
What we can't we look at it from a perspective of like looking at stiffness, like the intelligent compactor? Let's suppose we check the stiffness, then we can do some sort of a like we put a certain air void, and then we can quickly check the stiffness if it's mass, for example.
Do
the
a
deflection.
back calculation.
I mean the deflection, let's suppose deflection, not necessarily the stiffness. But you can check it from this model for a certain percentage air void, or like you can do sensitivity analysis for parameters that might match whatever deflection that you get from there. Because at the end of the day, density is important, but I mean I think stiffness or deflection is the one that represents the actual response of the layer. So you might like just do sensitivity analysis check, which maybe not air void, maybe also like some sort of also bonding between the aggregate too.
Yeah, this is actually applicable because we can do different gradations in DEM, and we already know their mass and their like area.
I
So,
think
we
like
can see-
the deflection can be a good representation.
Right, and then we can get those from DEM and like establish a database, and then we can do the calculations based on that database.
Yeah, matching the gradation is not a problem. How do you get the initial void ratio predicted right of what is in the field?
Well, I don't know, but do people use sound, maybe?
Acoustic.
Sound to determine the void ratio or to
Well,
correlate?
that's a good suggestion. I don't think that it's been tried yet.
Maybe sand?
I know this question came up big time when Professor Al-Qadi and I started our first research on GPR with GSSI folks
so
on this.
the real ballast one.
For the ballast, right?
Fouling
Ballast
thing.
fouling and detection. And there were two different thoughts about, how is that image, the reflection coming?
Uh-huh.
Is that because of the large voids or the large particles? What's the reflection caused by it? So there's still unknowns about that, and I mean that's a great
Because
research topic in my
the reason I brought GPR is because, especially the moisture, it will have a very distinct frequency component.
I mean, this is freely grading material. Don't think about moisture. Of course, all ballast will accumulate
Okay.
moisture and all that.
So it's like big stones versus the air. They will have different frequency responses in the signal. If we can like isolate different frequency components using some digital signal processing methods, maybe we should have a try, or maybe it's some way that we can work. It's just a suggestion or a thinking.
Again, there's a big need for it. There's nothing out there available.
Let's write a paper.
You guys are smart, and these are excellent questions you bring up. I know the interest, but I tell you, this is the most challenging thing right now. There's no clue.
Right now, how do you measure, like how do you stop that you have to stop?
That's the question for years I've been asking. Like, they have stabilizers, right? When they put new ballast, okay, they come and do stabilizer
Yeah.
shaking, and then some guy decides that that's enough. Okay, it's done. It's done, but what means? How do you
Yeah,
measure? How do you say this? It's like by experience. Okay, it's done. Let's move on. So we don't know what's the void ratio density. Nothing.
I mean, if let's say it's compact, since ballast is mostly one size particles, right? And if it's compacted the maximum, but we don't know the density. But let's say if we can know if it's compacted the maximum, then we can find out the density by, let's say, lab measurements, because you can do lab measurements to get rodded unit weights. We do it for our mixes.
Like the box again, he was packing things at the QP and the large rocks and everything.
Yes.
So, but he did also packing studies like that using DEM again. But how do you relate that to the field condition?
Like using a NDT method, let's say not only TPR, maybe some mechanical wave-based method, and run a lab test using pretty much the
Yeah, I
same
talked to many
thing.
people like Professor Popovic, Professor Rees. Those are, they're experts in non-destructive techniques.
Yeah.
But the porous, very porous nature of that layer,
Uh-huh.
I mean, nothing works really. A sound we never thought about yet. That's one thing, ultrasonic or whatever.
Yeah.
Some sound waves, right?
Yeah. Or pulse load.
There's something that we were gonna try to do.
But Professor, like the question is, whenever we're talking about density as a way to check the quality at the end before stopping, is density will show you everything?
Yeah, see, that's a good point too. Maybe it's like a quick plate test, plate load test, kind of how much deflection they're getting for a standard load. Maybe that's the way to assess it's done, right? Because you can, in the lab, you can relate that to different void ratios, densities.
Because density many times can hide many things, because you're taking it over volume.
You don't have a QC, whatever, or QA, whatever type of approach to say that. That's the way.
Any other question? Thank you so much for the
Again, interesting, so that's why I posed that question. That's really someone.
Yeah, I mean, the presentation was very good.
No, see, we do.
Oh, okay.
We do and single, we're looking for single.
They don't have like the full summary.
Okay, so you know the position of the particle?
This is the one that you had the picture, right?
But again, there's no like
Yeah,
Send us the
Something wrong with the
This is my one can tell you. It's not about the version of the letter.
Okay, and then you said the rotation.
Yes, the rotation.
So say you can go.
I don't watch.
This is like this, where there's
I think what she does, I mean, I'm not exactly sure what she did for this, but she reads it
I
and
was
she makes
expecting,
something
you know,
very
strain
simple.
and stress, but then
Like
from
usually
where?
No, that's because you can see this is rigid, so you cannot really have it. It's not like a cell.
Yeah, exactly. How do you?
No, it's not really.
It's then an accelerator.
Yeah.
It knows, it always knows which direction it's up,
Right.
and that's it, right? The
Is
rest
that
you can
small
find.
road like from Shanghai's?
Yeah, like this is from his province.
Ah, okay.
Thank you.
There's a big guy also graduated from here. You'll meet him in TRB.
You introduce him to me.
Oh yeah, oh yes. 好久没见了，得听你的多多包包怎么见到你。啊，行，你现在就做地点吧。
就玩电脑。
玩电脑，挺好。做实验参考这个。哎，你让那个 preliminary 什么时候考？
我qualify
啊？第三没考。
qualify
你是什么时候？
second year。
我们是同一年来的，对吧？
我是
第四啊，第四个。
And same with abstract.
啊对。
You're in charge, right?
不是，我是
Yes, but I know
17年的下半年。
maybe in November working on like the
那时候呢，我还不是，我是18年的时候，
we stopped actually
差不多